Okay, so welcome everyone. Those of you who are attending online live lectures and those who will see the recording. So before going, I want to make a little comment about the recent news that created, I'm sure you've seen it, that created of noise in the physics community. If you remember when we were talking about the spin-orbit interaction, let me put my pointer here. We discussed about factors of 2. I told you that the spin-orbit interaction between the magnetic moment of the electron associated to its 1/2 spin and the magnetic field that the electron sees as it rotates the nucleus. So it sees essentially sitting with the electron, you see the nucleus rotating, and this is a current that creates a magnetic field. And in order to calculate the magnetic moment of the electron, you can use standard electrodynamics, and you see that the expression that is given, for example, in Jackson's book, the magnetic moment of a particle of charge q, which is rotating with an angular momentum L, is given by this expression. And I told you actually this is not true for the electrons. There is a factor of 2 in the numerator of this expression, so the magnetic moment of the electron is twice as large as you would expect for a spin 1/2 particle. And this is explained by Dirac's equation. It gives you exactly a factor of 2. Experimentally, actually, is not a factor of 2, is this number that you see over here, a little bit more than 2. Recently, I mean, the muon is the heavier cousin of the electron. It's a lepton. It interacts with electroweak interactions with neutrinos, electrons, and same calculation, the same type of calculations that have been done originally by Feynman, Tomonaga, and Schwinger with quantum electrodynamics. They gave a different value for the magnetic moment of the electron. So this is called the G factor, which is the ratio between what you have and what you expect, essentially, and what you would expect from a conventional Dirac equation. You can do the same calculation for the muon, and you find a particular number. And now experiments, which have been done at Brookhaven, at Fermilab, there are some experiments going on at CERN in Geneva as well. They show that actually this number is not quite what the theory predicts. And so great excitement. This deviation of this factor of G mu or G electron from 2 is caused by the fact that when the electron or the muon move around, they also can create virtual pairs, electron-positron, muon-antimuon, and this, the technical term is dresses the particle, and so it changes the magnetic moment. And so there's great excitement about this. So we don't know, there are speculations that if the results are true, they're not quite there to the 5 sigma uncertainty that is usually demanded. It's 4.2, getting there, but not quite there. So there is 1 in 40,000 chance that this result is actually a fluke, a random fluke of a combination of experimental uncertainties and errors. But if this stands, then there are speculations that there might be a new force in nature that hadn't been seen before ever, a 5th force. So the truth evolves in time. Whatever I tell you has to be understood as that's what we know now, always subject to correction. So although this may seem not to affect us at all, clearly, if you want to calculate the spin-orbit interaction, you don't have to worry about how many digits do we have here. Quite a few. We never require such a extremely high level of precision. But in practice, in principle, it matters. So keep in mind that the truth evolves in time. What we know about reality, it's changing. So let's go back to our things. So we talked about second quantization in the past few lectures, and elementary excitations. We saw the quantization of the Schrödinger field, which is not really, well, it's an excitation if you consider that the ground state of a Schrödinger field is no particles around. We saw the example of plasmons or phonons, and then just to use, to show another example of the same machinery, Lagrangian and Hamiltonian formulation of fields, canonical quantizations, we saw the quantization of the electromagnetic field, how it follows essentially the same procedure. We will have to talk about electron scattering in solids, and that's something that we may start dealing with at the end of today's lecture, the second part of the lecture. But we were dealing with dielectric screening, which is something that we have to deal with before considering the interaction of electrons that move in a crystal, which is what we really need in order to understand charge transport in electronic devices. We need to understand how a perturbation caused by phonon, caused by other electrons, is affected by the fact that there are many other electrons around, and this perturbation can also polarize the ions of the crystal. So before we can consider scattering, we have to understand how free carriers and the ionic excitations themselves can modify this potential and screen it. And I'll review briefly what we did last time. We started talking about the fact that we're going to use just Poisson equation. We really don't solve Maxwell's equation here because the time scales that we're interested in about transport, switching of devices, usually are slow enough so that we can ignore what's called retardation. We'll be dealing with optical transitions, so you may worry about what happens in that case, but even in that case, the momentum of the photon which is absorbed or emitted is so small compared to the momentum scale or the wave vector scales that we have in a crystal that we don't have to worry about that. We use the random phase approximation, which I gave you last time an example of a general form of the transverse function of a system. You perturb a black box with some perturbation, you split it into its Fourier components. If the perturbation is sufficiently weak, in our case, if the electrostatic potential that we apply or the fields that we apply are much weaker than the electrostatic potential and the fields that keep the crystal together, the interionic, interelectronic interactions, then we can assume that we can linearize the response of the system. And so the transverse function is what we're after. And we call this transverse function the dielectric function in this particular case. So what we do is we apply an external perturbation. We look at one wavelength and one spatial frequency at the time, what we call the random phase approximation. Wavelengths and frequencies do not mix in these approximations that we're using. Clearly, for example, nonlinear crystals, that's a nonlinear response. Frequency doublers, these kind of things, clearly they don't satisfy this requirement. They go beyond our theory. And we consider just the potential. If we apply an external potential, the system responds with a polarization potential. Charges redistribute, ions, electrons, and we express this redistribution of the charges in terms of a function, our response function, which is the dielectric susceptibility, which is proportional to the total field that these charges will feel. Either the total field or just external field. I mentioned a little bit the difference between going from a fully self-consistent to a non-self-consistent random phase approximation. And we define the dielectric function in either of these forms. One thing that I didn't mention last time is this treatment, particularly for the electronic response, and I will mention it in a bit, is deals with the longitudinal response. The dielectric quantity here, in principle, is a tensor. We apply a field along one direction. The polarization that we get, let me put it over here. I don't know, I didn't have that slide. The polarization field that we have, in general, does not have to be parallel with the external field that we apply. I'll give you a simple example in a moment. Now, let me give you now. Simple example is, let me draw here. Let's see if we, pen. Suppose that you have, where am I here? Suppose that you have a silicon inversion layer. So this is your silicon, this is your oxide, whatever insulator you have. So electrons don't penetrate here. And you know that electrons are quantized in some states over here. And the wave function corresponding to the first subband will look something like this. The wave function corresponding to the second subband will look something like this. Now, suppose that I have this silicon inversion layer of my MOSFET at low temperature, and I apply a small field in the plane, so down towards inside the plane of the screen. The field may be small enough to allow for our treatment about linear response. Our assumption of linear response is still valid, but maybe, particularly if the confining field, the gate bias that we apply here is not large enough, the separation, the energetic separation about two subbands will be quite small. In this case, let me go back to my pointer here. If the separation is small, what happens is that the electric field may excite some electrons. Suppose that I apply an AC field. Electrons move back and forth inside the plane, so they go inwards and outwards of the plane. But if the field is large enough to excite the carriers from a first subband to the second subband, what I have is a redistribution of the electrons, so the electronic charge in the inversion layer, which is not only in the plane, but also along this direction. So if I call z the direction in the plane and x this direction, my epsilon will have an xz component which is non-zero. So I apply the field in one direction, but the charge, actually, the polarization charge actually is along the another direction. So if I look only at the potential, I cannot capture this. I would have to go and complicate my picture by looking at the electric field, the D field and the E field. Here I'm just looking at the gradient. I'm assuming that the polarization is parallel to the external field that I'm applying. So that's something that I should have emphasized last time, and I forgot to do it. Okay, so we look first at two components of this dielectric susceptibility. This object is, first of all, a function of wavelength and frequency. I gave you the example of water molecules. If the frequency of the field, that external perturbation that I apply, is so high that the molecules do not have time to rotate or polarize, then clearly I expect this susceptibility to go to zero at very high frequencies. Similarly, if the perturbation that I apply changes spatially over a distance, significantly over a distance which is smaller than the size of the molecule will not rotate anymore. It may polarize, that's the electronic response, but it will not polarize, it will not respond. So in general, I expect chi go to zero or epsilon go to the static or long wavelength response, when the short wavelength response, when Q or omega go to infinity, will become very large. And that is something that we will see. Now, this chi is due to two effects. Ions can polarize and electrons can polarize. So we separated the two things, and the first thing that we looked was the ionic response. We took hint from something that we had already seen before, so this is the third time that I'm showing you this slide of a linear chain. We consider this linear chain and look at the phonons, so the eigenmodes of this system. But now what we're going to do is apply an electric field and see how these ions, let's assume that the black ion and the red ion have different charges. So it's an ionic material, it's a polar material with some charge transfer between the two when the bonds are formed. And we see how they polarize, which is how their distance, the relative distance changes. This creates a dipole. It's our polarization field, which is induced by this dipole, and how it behaves in frequency. We'll consider for the ionic response only the long wavelength case. The general case actually is extremely complicated. I guess nowadays you can do it with density functional theory, and in most materials, there's not a big dependence on the wavelengths in the range of wavelengths in which we're interested in. So we looked at originally at phonons, but now we look at these equations, the secular equations, how we can extract the frequency of the phonons. But now what we do is we add an electric field. So assuming that the big ion M and the little m have different charges, they feel the electric field with a different sign. And then if we look at their difference of the two displacements of the two ions, we see that we can express it as essentially a harmonic oscillator with a resonance. In this case, of course, the resonance is really a singularity because we're assuming that there is no lifetime for the phonons. And so we see that the system responds, and we can write the dielectric response or the response of the ions, having written the polarization in terms of the density of dipoles that we have per unit volume and the eigenfrequency of the system, which is the frequency of the optical phonon. In a one-dimensional chain, linear chain is only an optical phonon. In 3 dimensions, this will be actually the frequency of one of the transverse optical phonons. We can write the dielectric function as something that at omega equals to infinity goes to some value. This is where the electronic polarizability will come in. Electrons are lighter, they respond at a higher frequency. But as the frequency drops and it goes towards zero, the dielectric function increases, going through a dip, a negative dip, and then a positive. It shoots down and up, and then it comes down to a value which is bigger than the dielectric response at high frequency, because now at a frequency which is sufficiently small, smaller than the TO frequency, the ions can polarize. And I gave you also a general argument, which is important, that the zero of the dielectric functions are the longitudinal modes. So we can write this expression in these terms by solving, setting epsilon ion of omega equals to 0. The omega at which this occurs is, by definition, the frequency of the longitudinal optical phonon. So we can write this the dielectric function due to the ionic response also in this form. These two are equivalent, and the omega LO is expressed in terms of the omega TO via the Lydane-Sachs-Teller relation. In dealing with this situation, we also saw that electrons can interact only with longitudinal modes. This is not restricted to ions. It's true also for electronic motions. For example, electrons can interact with plasmons because they're longitudinal waves. But they do not interact in a Coulomb way, in a polar interaction with transverse phonons, for example, because the microscopic internal electric field that you have at the transverse frequency is zero, has to vanish because of the relationship. And I gave you this argument last time. It's a very general argument. It's a little bit idealized. In real life, you never have purely longitudinal, purely transverse modes. Usually, you may have situations which you have them, but they mix at particular phonons. They mix quite a bit as soon as you move away from the center of the Brillouin zone, and actually at the edge of the zone, the wavelength is so short that it doesn't even make sense to split optical and acoustic phonons. Okay. This is regarding the simple model for the ionic response. So remember, we can write the dielectric function due to the ionic response as the dielectric frequency, the electric function that you have at a frequency much larger than the frequency of the phonons. Infinity here means much bigger than omega TO. And then there is a step as you go down in frequency with an up and down step, in which the dielectric function increases because now the ions in the crystal polarize. Now we have to deal with the electrons. In our examples of water, the water molecule can not only rotate, but can also distort. And the distortion is due to an ionic component. The oxygen and the hydrogen nuclei change their distance, but the electrons, the electron clouds that constitute the molecule, the bond, also polarizes. Electrons will go towards the positive plate of the capacitor that gives the electric field that we're applying, and move away from the negative plate. So we have to deal with the electronic response. Again, I should have said, and I said it today, but I should have said it last time, we're dealing with a longitudinal response, and we also assume for now quasi-equilibrium of the distribution of the electrons. Off equilibrium, the electric response is a tricky business, and we will not discuss it. So again, we have to use the same thing. So we want to write the total potential as the sum of the external and the polarization potential, and we want to define the dielectric function due to the electrons as essentially the ratio between the total potential and the external potential that I apply, so that when I'm dealing with electron scattering, for example, all I have to know is the electronic external potential, and the polarization will be implicitly accounted for by the dielectric function that I will put in my expression for the perturbation. The strategy that we followed was the following. So we used the random phase approximation. So we decompose the external perturbation into its Fourier components, both spatially and temporally. And then we look at one component at a time. I'm not sure why I didn't put the little omega here, but this depends on time as well. And then we define, as I said, the relative dielectric function by this expression. So we express the total perturbation that the electron field as the external potential divided by the electric constant by moving this on the left-hand side. Again, random phase approximation, because we're going to look at one frequency spatially or in time at the time. They don't mix. If I perturb the system at a given wavelength, the system will respond at the same wavelength with a different amplitude, which is what epsilon gives us, but at the same wavelength. Similarly, if I perturb the system at a given frequency, the system will respond at the same frequency. The idea is we have to calculate now the potential due to the polarization charge. So we calculate the polarization charge in a way that I'll describe in a minute by looking again at its Fourier components one at a time. So the idea, as I said, in the literature, most of the derivations use Green's functions. Here what we do is we consider the perturbation of the wave function. The charge, the polarization charge, is the, I take all of the states which are occupied in a crystal. I look at the difference between the charge distribution before and after I apply the perturbation. The charge distribution is given by the square of the wave function of each state, occupied state, summed over the all occupied states. So if I look at the change of the wave function by using perturbation theory, I can isolate the contribution which is due to the external potential and will be proportional to the external potential. One frequency, Q and omega at the time. So I use my block functions, and then I look at what is the change of the block function which is caused by the external potential, and this is given by just the conventional first order perturbation theory, time dependent, okay? So there is an omega here, and we'll talk about this little factor. So this is the new wave function. New means perturbed. Here I have matrix element of the external potential, or total potential if you do a self-consistent calculation. This is its complex conjugate. So if I take the square of this will give me the total charge after the perturbation. I want only the change of the charge. So essentially, by taking the product of these two, I will consider only the terms which are linear in delta psi, because they are linear in the potential. And so we'll have a term which is the delta psi star plus its complex conjugate, psi delta psi star. The terms which is containing the square of the delta psi is proportional to the square of the external potential. And this is a nonlinear part of the response, and I'll ignore it because we're dealing with a linear response. We can calculate relatively simply the matrix element of the external potential over block functions. If we were in free space, if this were an electron gas in free space, this will be trivial. It will be just a Fourier component k minus k prime of the external potential. Now I have to drag along this complicated object, which is the matrix element of the plane wave over the periodic component of the block function, if you want. This accounts for the fact that I have to deal with the atomic orbitals that constitute my crystal. So I can write the charge by summing this change of the wave functions that I wrote over here, just the perturbation term over all occupied states, p, k, or mu. Mu is a band index, k is the k vector, and p is the probability, the occupation, 0, 1, or a state, or in between if I use statistical mechanics at finite temperatures. This might be the Fermi-Dirac distribution, is the probability that a state is occupied. If I add this thing, I get my perturbation charge, my perturbed charge, which is this object. I can write it do a little bit of an algebraic manipulations here, and I get a rather messy expression that we will discuss in a moment, excuse me, for the perturbation charge. This is already in terms of Fourier components. You see that I get e to the minus IQR here, so I can identify this beast over here if I look at what did I write here with the delta rho q that I wrote in this term. The e to the I omega t is implicitly in there.
Ciao.
Okay. Hello. Okay, so we see what the polarization charge is. If we know the Fourier component of the polarization charge, remember we're using a static approach, adiabatic if you wish, no retardation. I can use Poisson equation to convert the Fourier components of the polarization charge to the Fourier components of the potential, and this will give me finally my, in this expression, will give me finally my dielectric function. I put it in a red box. This is an important expression. It's called Lindard dielectric function, or the Lindard expression for the dielectric function for a free electron gas in which this matrix element is actually unity. So it's it simplifies somewhat. This is just the only complication, if you want to look at it in a positive way. It's a relatively minor complication considering that we're dealing with a crystal, and instead we have a formula which is essentially identical to what we have for a free electron gas. We'll discuss, again, as I said before, a little bit this imaginary part that it's added over here. This is required to make this expression well behaved without any singularity. Indeed, you realize that I'm integrating over Q, sorry, I'm integrating over K over here, so I will hit eventually a pole of this expression when ek minus ek plus q is equal to minus h bar omega, I will get a singularity. So this regularizes the expression, and I'll tell you a little bit more. It's what's called, with a funny name that I never remember how to pronounce, Chokotsky-Pellergy theorem, which is the Kramers-Kronig relationship in terms of how a physicist would call it. Anyway, we'll talk in a moment about this. So this is the expression, which is exact in quotes. Remember the approximations we've made. This expresses only the longitudinal response, and it's a linear response. But within these two approximations, this is exact. The problem is how to handle it, what to do with it. So I'll give you several examples of limiting cases which are of particular importance and that we will use in dealing with scattering. The first example is the static dielectric constant. So we assume that I have an intrinsic dielectric, an intrinsic semiconductors, valence bands completely full, conduction bands completely empty. What is the electronic response of this system? This will give us the dielectric constant. It will be the static dielectric constant for non-polar insulators or dielectrics, because ionic response is 0 in that case. For polar materials like three-fan compound semiconductors or many insulators like silicon dioxide, hafnium dioxide, it will be just the electronic response, which is the dominant part. There will be an additional component due to the ionic response that has to be added. The second example that I will give you, we'll move to the response of the free carriers. The second example will be to look at the static response of free carriers as a function of Q. So we will set omega equals to 0 and see what happens when we do that when Q changes and it's small. We will deal later on with corrections. The third example will be what happens to the dynamic response of the free carriers at q equals 0. So we will essentially set q equals 0, or expanding powers of q here, and look at what happens in terms of its dynamic response. And this will give us the plasma response of the free carriers. Finally, I don't know how long I should spend, how much time I should spend on dealing with the general expression. Dealing with this complicated, essentially it's an integral, in general cannot be done. If I have a degenerate system, I have to do numerical techniques. I'll show you some numerical results for silicon. In a non-degenerate limit, in which I can approximate these probability p's with Boltzmann distributions, then it can be done analytically. It's not easy. It's not fun to do it. I have slides with the entire algebra. I'll go quickly through it to show you how painful it is. Eventually, you'll get some corrections, which tell you, particularly at large Q, or Q which are not very small, how, for example, the static response of free carriers changes. And in general, as I told you originally, but very large Q, we expect this epsilon, the electronic component, to go towards the no response of the carriers, 1 or epsilon vacuum or whatever. Okay, so let's start with the first example, which is the static dielectric constant. So what we assume is that this probability P in general will be given by the P0, which is what we have at 0 temperature, valence bands completely filled, so P0 K nu is equal to 1 for any K when mu is one of the valence bands, and 0 when mu is one of the conduction bands. And in principle, we can have the response of free carriers. So the first example will be to set this F equal to 0, an intrinsic dielectric, no carriers, no doping, or a wide bandgap material that doesn't have, like silicon dioxide, that doesn't have free electrons, or an extremely small amounts that we can ignore. So we'll set with this approximation. Then it simplifies because we can do the sum only between the conduction and the valence bands. The mu is only the valence bands. The mu prime would be only the conduction bands. Otherwise, this thing goes to 0. We have to worry about what happens. This is the nasty thing. One important rule, which I do not prove, is that if you take a particular state, you sum over all other possible eigenstates of the system, our plane waves, essentially our block waves. And we multiply the matrix element of a plane wave, e to the IQR, between these two states by the difference in energy between the two states. And we add them all up, we take the square of these matrix elements, we get this expression, if you want, the parabolic expression. M is the free electron mass, of course. It's a famous sum rule. It's not too difficult to prove it, but let's leave it at that. In our case, if we look and we set here, we sum over all between a valence band and a conduction band. The term which we have here, if we bring this stuff in the denominator, is the term, the dominant here will be the smallest term, which is essentially the gap. This is the direct gap. It's the difference between K and K prime when Q is relatively small, okay? So we have that we can write the sum over G, which is the sum over all the final states of our matrix element T to the IQR in this form. And then the integration becomes extremely simple because this becomes a constant. Here we are taking a gap, so we're simply summing over the density of the electrons. And this is approximately true because the term in the sum that contributes the most is the term in which this is the smallest term. Remember, it's static, so omega equals 0. Let's ignore this term for now. This is the gap, the direct gap, some average of the gap over the Brillouin zone. So that's why there is the little wiggle over here. It's approximately true. It works quite well. The general rule that you see is that materials that have a large band gap have a smaller dielectric constant. So, for example, the search for insulators which have a higher dielectric constant is tricky. You see that electronically you don't quite get there. You need a strong ionic response because the electrons actually give you the opposite. If you increase the gap, if you decrease the gap, you get a higher electric constant and vice versa. And of course, if you want a high K, a high epsilon, you'll get a small gap, and at some point, it's not an insulator anymore. This object here is essentially the sum of what's left over from these expressions. It's the plasma frequency of the valence electrons. This is a relatively large number, of the order of 10 electron volts, expressing in units of energy. Notice that this is the density of the valence electron. You can calculate it if you know the unit cell that you have in a crystal. You can calculate how many valence electrons you have, and then you can calculate the plasma frequency. You can estimate the direct gap of the material, and this works quite well quantitatively. Not perfect. I don't remember the number, but for silicon dioxide we get something between 3 and 4, which is pretty good. For silicon, you get, or any of semiconductor with a gap of the order of 3, which is the direct gap of most semiconductors, even 3.5s, because it's an average gap of the Brillouin zone, and you get something of the order of 10, which is roughly what you have. Silicon is about 12, and germanium about 16, because the gap is smaller, so epsilon goes up. And some 3.5 with a small band gap have a higher dielectric constant, exactly because the gap is small. So this is a general rule that it's interesting to know, and it's good to know. Okay, so this is regarding the fact, I remind you, we set this F equals to 0. We said I have no free carriers. Now let's do the opposite. So we can ignore this P0. It's lumped into the response that we just calculated. So essentially what we'll have to do is we replace this epsilon 0 with the static dielectric constant of the material. And this will lump already the effects of all the P0. Convince yourself that you can do that, actually. Okay, so what we do is, where am I here? I'm here, okay? So what we do is now consider the response only in the free carriers, and consider that Q is not too big. And not too big means, compared to the G vectors, is not very large. I'm summing over these G's. I have an interaction between a matrix element between a K and a K plus Q plus G. If Q is very small, I can approximate this Q over here. I can ignore it, set it to 0. So essentially here I have unity, and this is roughly, gives me roughly unity. Okay, so I recover, in the case of free carriers, what we call the Lindart form. Okay, I've gotten rid of this nasty object. Okay, so what I'm left with is just this. The P's have been replaced by the F, and the F now will be the Fermi-Dirac distribution that I have at equilibrium at a given temperature. Okay, so one first way to deal with this is in a static limit, we can show that these are static. So the static response of the free carriers, when I set this omega equals to 0, I want to write it in this form. I take away an epsilon s, which is the static dielectric constant of the semiconductor. So I multiply epsilon s if you want. I bring whatever is left inside a square bracket, and I call whatever is left, which is this object, the sum over k, what's inside the sum and the square divided by epsilon s, I call it beta squared. And I call this the screening wave vector squared. Sometimes it's called the screening parameter squared. The inverse of this thing is called the screening length. Notice that this beta has the dimension of 1 over length. And the length that it expresses is the screening length. That physically means it is the distance from a particular charge, which is my perturbing charge, beyond which the perturbation is not felt much anymore. And that's because if I have a positive charge, free carriers, free electrons will go towards the positive charge. If I have a negative charge, they will go away. So, sorry, vice versa, negative charge, they will go away. So at large distances, I will not feel the potential, the perturbation anymore. So this is the physical meaning of this object. This is relatively simple to calculate. I will give you some examples. So this is just a rewriting, a definition of what beta is is whatever you have to do in order to convert this equation 503 into 504. And we'll calculate it now in particular limits in which omega is equal to 0, and then we'll look at a case in which Q instead is very small. So we have a final answer of our problem in this way now, that the perturbation potential, sorry, the total potential that electrons feel as perturbation when they move in a crystal can be expressed in its Fourier components. And the Fourier components of this potential are nothing but, by construction, how we constructed is epsilon r, the external potential that I usually know what it is, divided by the electric function, which lumps what I didn't know originally, which is the polarization response. So how do I calculate now this beta in some particular cases so that I can have an expression that I can use and calculate explicitly? So what we do is, the first thing is to calculate what's called the Debye-Huckel. If I look at the non-degenerate limit, Thomas Fermi screening, if I look at the general case, what we do is we consider this expression only when Q is not too large. So what we can do is we can expand f of k plus q and e of k plus q as a Taylor series in powers of q, and retain only the leading order terms, the terms that we need to proceed. So essentially what we can write is e of k plus q minus e of k as q times the gradient. Similarly for f, the 0, I've added a 0 here, meaning this is the equilibrium Fermi-Dirac distribution. So the net result is that, notice that this is the sum over k. I can convert the sum over k to an integral of the Brillouin zone. An integral over k can be converted to an integral over energy multiplied by the density of states in the isotropic approximation. And I get essentially that there is a cancellation. This is a term in the numerator. This is a term in the denominator. Essentially what I have is a cancellation of the q dot gradient. I'm left with the derivative of the Fermi function equilibrium with respect to the energy. And then there is this factor E squared divided by Q squared that I have in front. Okay, and the epsilon s has been multiplied by for now. So I can write it this way. So this will be essentially my beta squared. Okay. Now my beta squared is given by this, and this is nothing but if you look at what the Fermi function is, if I take the derivative of the Fermi function with respect to the Fermi energy, this will be equal to I can take the derivative out because this does not depend on the Fermi energy, so I can get it out of the integral. I'm left with the integral over the density of states of d times f0v, which is the total density of the free carriers. So my beta square, my screening length, is given by this factor E squared over epsilon static multiplied by the derivative of the density with respect to the Fermi energy. In a non-degenerate limit, the density is just the exponential of e to the minus ef over kt. So what I'm left with just a kt in the denominator. So I have that the square screening parameter in a non-degenerate limit is given by an expression that grows with density. Take the inverse of this. This means that the distance over which the potential is not felt gets shorter and shorter as the density increases, which makes sense. As I have more free carriers that can screen my perturbing charge, for example, it's static, so it's an impurity sitting there, for example, charge impurity. The higher the density, the stronger will be the screening effect. The screening length will get shorter. Notice that instead the screening gets weaker as the temperature grows. This has a relatively simple meaning, physical interpretation. Free carriers are subject to thermal excitation, thermal motion. If you have a positive charge, for example, electrons would like to stay close to this positive charge, but if you increase the temperature, the random thermal motion gets faster and faster, so they tend to spread less densely around the impurity, spread a little bit farther away. So screening effects increase as the temperature goes down, carriers stay put next to the perturbation charge. As the temperature increases, carriers don't stay as well put anymore, and they move farther away, and screening gets weaker. This is roughly the same behavior that you see also in the degenerate limit, but it's less clear. Okay, in the extreme case in which you have a total degenerate gas, like at zero temperature, in which the derivative of the Fermi function is just a delta function of the Fermi energy, then you get something which still depends on n. Really doesn't depend on temperature anymore because we have assumed that the temperature is zero. But again, there is a dependence on the density also at the Fermi level. Okay, so this is the general expression that we will use a lot. It will be used, for example, to screen impurities. If you look at what the potential looks like in real space, you will have a potential which has a Yukawa form. So it will not be 1 over r, but it will be 1 over r multiplied by e to the minus beta r. This is the Debye-Huckel or Thomas Fermi screening length. So it shows that you have a potential that has still a singularity at r equals 0, 1 over r, but as r increases, if you go away from the charge, then the potential decays exponentially with a decay constant spatial, that is the screening length. Okay, let's take the opposite limit, if there are no questions. So we've looked at, where are we here? So we have considered this. We consider the case in which omega equals 0 and q is not too large. I will show you later on what corrections you have, at least qualitatively. At large q, this beta actually decreases from what the Thomas Fermi or the Debye-Huckel expressions are. We'll show it in a non-degenerate limit. As I said, the degenerate limit cannot be dealt with by hand or analytically exactly. But in the non-degenerate limit, although complicated, it can be dealt with in enclosed form, I should say, not analytically, because we will have a funny function, a plasma dispersion function, that can be calculated only numerically. Anyway, so there will be some corrections. If we go beyond this expression, this approximation over here, which is a small q expanding as a Taylor series in q, we have some corrections which will decrease the effect of screening, as we expect. Now we consider the opposite case, in which now we'll set q equals 0. We'll take this q equals 0 limit and consider instead what happens in terms of the frequency dependence of this object. So what we do is we split the sum that I have over here. Let's see, we split it into two terms explicitly, fk divided by this minus fk plus q divided by the denominator, which is what I've written here. And let's do a little bit of a trickery. In the second term, we'll write k plus q as minus k prime, okay? And so we've done a change of variable here. So now, assuming that I have a symmetric, mirror symmetric band structure in isotropic case, for example, we have this property. So I can rearrange these terms in this form. Well, the only difference is that I have a k plus q and a k prime over q over here. So relabeling as k equals k prime in k, this is a dumb integration variable or some variable in this expression, we can simply write it this way, okay? Where I have the same denominator, except that the plus q goes from one term to the other. I'm assuming only one band, by the way, for simplicity, the band in which my free carriers lie. Okay, so I can rewrite this over here, and I can manipulate a little bit this object by extracting the ek minus ek plus q from here as theoretic as a square, and I can rewrite it in this form. So this is what I have for explicit dependence on omega, and so far I have not done anything to perturb my system except considering only one band and having assumed that I have spherical symmetry over here. I should say mirror symmetry. I do the same now. I take a relatively small q. Notice that now I have to be a little bit careful, because if I take only the first order term in q, I get nothing. So I have to go to second order in q. And then I can rewrite this entire expression in this particular form. Okay. Again, if I take only the first order term, if I integrate over all the k's, I get 0 because of the symmetry property that I have here. So the leading order term is of the order of q squared. Now notice that q squared and q squared cancel, and I'm left here with the sum of k over k of the Fermi-Dirac distribution of my free carriers. This is just the density of the free carriers. So what I'm left is E squared divided by epsilon, the q squared go away, I have a mass in the denominator, and then I will have a density in the numerator. This is just the square of the plasma frequency, okay? And this is the, I hope you remember what the plasma frequency is. We talked about plasmons, and indeed, in a limit of long wavelengths, we'll have to be a little more precise later on dealing with electron-electron interaction, some limits on the wavelength in which plasmons exist. There are processes in which plasmon decay, so we'll have to worry about that. But in the region in which the plasmons exist, the dynamic response of carriers, the free carriers at long wavelengths, is given by this plasma response. By the way, notice that for the static response of the valence electrons, the static dielectric constant, we also had the plasma frequency, except that we had the gap over here for the frequency. Okay, so notice again at large frequencies we recover no response. Carriers stop responding. The plasma frequency in a semiconductor, say silicon numbers that I have in mind, it goes of course from 0 in intrinsic silicon to, I think, at 10 to the 21st electrons per cubic centimeter is about 0.2 electron volts to 100 MeV. So they're relatively fast frequencies, but they can go as low as you wish. This is particularly important. We will deal with dynamic screening in some particular cases. So the rule of thumb that we can get from this important relationship is that when the frequency of the excitation, the perturbation that I'm applying to the system is smaller than the plasma frequency, then electrons respond, and it's not a terrible approximation to assume that they respond statically with the Thomas Fermi or Debye-Huckel expression that we derived before. If the frequency of the perturbation that I'm applying is larger than the plasma frequency, then the free carriers cannot respond anymore. So it's not a terrible approximation to assume that the perturbation is unscreened, is left unscreened. Of course, you can do better by smearing out the transition between these two extreme limits. But as a rule of thumb, to understand what happens, so if you have an optical phonon of a frequency, say gallium arsenide, 36 semi-electron volts, or some material that has an optical phonon of a frequency of several tens of milli-electron volts. If the plasma frequency, so if the density of the electrons is sufficiently small, the interaction, the optical phonon and the interaction of the electrons with these optical phonons can be left unscreened. The phonon oscillates too quickly for the electrons to respond. If instead you increase the electron density and you increase the plasma frequency beyond the frequency of the longitudinal optical phonon that you're dealing with, then the interaction can be considered statically screened. And this is true for any type of interaction that you have. An electromagnetic wave, some time-dependent potential that you apply to the crystal, or whatever. So this, let me remind you what we found. The three-boxed equation, the static dielectric constant, they all come from our messy expression here in some particular cases. This is the static dielectric constant of a crystal, so it's the response of the valence electrons. Again, to get the real static dielectric constant, you have to add the ionic response too, of course. This is the static response of free carriers, where this epsilon s is whatever we just calculated before in the previous boxed equation. And then we consider what happens when instead we look at the long wavelength behavior and dynamic behavior of the free carriers. Okay, this is what time is it? Let's keep going for a little bit. The general form. The general form is kind of messy. So first of all, we have to go back here. So I have to integrate this object, right? This has the sum over G that I can deal with by using my sum rules if I want. I have a sum over bands, okay. I can consider the bands which matter the most, which minimize the denominator. I have free carriers though, so I have to consider also, I apologize, my 10 o'clock clock. That's doing its things. Okay, good. And then I have an integral over k. And again, I told you I may have issues here. I have a pole. So when I have a pole, we have to go back to, I hope you remember, calculus of residues. So let me jump actually to what we do, and then we'll tell you the results. So we have to do the integral, which has this form. It's an integral over x of x minus x naught. X will be my e of k. Sorry, x naught will be my e of, sorry, x naught will be some omega. My x will be this object. I'm integrating over this energy. So I have to deal with this. And the usual thing is, I hope you consider it usual, is to use the calculus of residues. So you are integrating this function over the real axis. So what you do is you have a singularity at this point. The theorem, once I taught a class here, there was a Polish student and he told me how to pronounce these things. I'm not going to try, particularly the second name. Let's call it the Kramers-Kronig relationship, which is what the physicists call it in practice. So the theorem says that if you want to integrate this function, the result will be a real part, which is called the principal part of the integral, and it will have an imaginary part, which will be minus or plus, depending on the sign that you decide to use here, an imaginary part which is proportional to the delta function, x minus x naught, multiplied by pi, which is an important pi. It's where the 2 pi over h bar of your Fermi-Golden rule can come from, so it's an important pi. The way to do it would be to integrate over a contour which goes over the entire real axis, avoiding the pole, so going a little bit around the singularity, the pole that you have here, and then closing the loop either in the upper half plane or in the lower half plane, depending on the sign that you choose here. If you do that, if the function that you want to integrate over, that you're supposed to integrate, which will be, again, my f, my p's, whatever. I have it here, for example. If this function goes to 0 sufficiently fast, which it does, these are Fermi-Dirac distribution. So at large k and large energy, they go to 0 exponentially. So if that function goes to 0 sufficiently fast, then the integration over the upper half of the plane, this half circle, which I let go to infinity, will give me a 0 contribution. The entire integral over the loop will give me 2 pi I times the residue of the function over here, okay, which will be in this particular case f, okay, and then I will have, I forgot, x minus x, whatever here. So I can do this integration, and this contribution goes to 0. So I'm left with the fact that the integral over the entire real axis will be an integral over whatever is the leftover from having cut this little piece, and the integral over half the circle around the singularity. I can do the integration either on an upper half circle or lower half circle, and that depends on the sign that I choose here. The equivalent way to put it, and that's why I put this I eta, it will be, depending on whether I put a plus or a minus here, it's equivalent to moving the pole a little bit below the line, which is what I'm illustrating here, or a little above the real axis, which will be equivalent to closing the integration by going the lower half. infinitesimal circle. So we know that this is 0 by essentially the calculus of residues, okay? It has to be equal to 0. If I go around a loop which excludes the pole, you can convince yourself by doing the integration on a lower plane that you get the same thing. Okay, so what you do is essentially, this is the mathematical form that I used. The integral of that thing over the circle will be the integral on the first part of the real axis up to this point x0 minus eta. Then I integrate over x0 plus eta plus infinity, and then I have this little integral over the half circle going up or down. And then I have the integral over the infinite half plane. This object, this term and this term, combined together, are called the principal part of the Cauchy principal value of the integral. Actually, let me sketch it a little bit. This numerically can be calculated quite simply. If I have, let's see, where am I? If I have a singularity here, this is my point x0. So the denominator, 1 over x minus x0, it's something that will go to minus infinity, and then it comes back to plus infinity, and then it goes to 0 like 1 over x, of course. Okay. So the integral of 1, if I put instead of f of z, I set it to a constant, say 1. What I have is essentially the integral of this curve. Notice that, strictly speaking, the integral does not exist in a strictly Riemann sense, but the integral will give me a value which is equal to 0, because so this term here, the integral for minus infinity plus infinity of 1 divided by x minus x0, view it numerically. I discretize my x-axis by uniform mesh, symmetric around the point x0. Whenever, whenever I have a point which is at the left of x0 by a given amount, there will be the similar point at the right, and the value of the function here and here will be equal and opposite. So the integral will give me 0. So if I have now a function which is smooth, which is varying regularly around the point of x0, I will have some variation over here. So there will be now a little bit of an imbalance between the integral which I do on the right-hand side of a singularity and the integral that I do on the left-hand side. So they will cancel almost, not exactly anymore, which is what I have when this is a constant. So numerically, actually, if you have make the judicious choice of choosing a mesh which is not necessarily uniform but symmetric around the singularity, you can actually do the calculation very quickly. So the principal part is an easy thing to calculate numerically. Not so easy maybe from an analytic point of view. And then what I'm left is with the residue. And the residue will be minus I pi of f0, the residue around half of this. That's not 2 because I'm integrating over only a half. And I'm integrating, in this particular case, I'm integrating clockwise, so I need a minus, because the Cauchy theorem assumes a counterclockwise integration. And then I have the integral over the infinite loop, which is 0. So you see immediately at the end that the integral over the real axis will be equal to the residue that I have, which is the delta function, given by this, plus the principal part of the integral. So I hope that you're familiar with calculus residues and you follow this this derivation. This is you have the slides. I posted the slides, and you can look at it in detail. But the net result is that the integral that we have to deal with can be written as a principal part of this integral that numerically can be done. And then there is an I pi f. Remember that I can write it formally as I wrote it at the beginning, principal part plus or minus I pi delta. The plus or minus depending on whether you want to move this up and down. And this depends on, let me give you one example, depends on the physics that you have in mind. We didn't go to the derivation of Fermi-Golden rule in detail. I think we did a little bit quickly, but essentially what you end up with before getting there is to consider an integral of this sort. An integral of this sort, if you do the integration from minus infinity to t, will bring you down the denominator, which has exactly this form. And in order to regularize this integral, you have to add a little real part to this exponential, which, by the way, is the only term that breaks symmetry under time reversal. So it makes the system irreversible now, and indeed Fermi-Golden rule says that the wave function collapses and you lose reversibility. So anyway, you have to regularize this integral in this way, and you get your delta function exactly by performing this procedure. The dielectric functions have an imaginary in the real part, and they are related by these relationships as well that take the name of Kramers-Koenig relationships. So let's go back to what we can do. We can actually, where am I? Here. You can actually do this derivation. I think I've outlined it here in these slides. I don't think I want to burden you too much about how to do it, but this is the way I've expressed it in terms of a single band. I've ignored the G vectors, so I'm considering the linear expression. The sum of the G vectors we know how to deal with thanks to the sum rule that we saw before. And the bands, let's consider only one band. We can extend it later on to many bands. So this will be the valence band. For free carriers will be the conduction band. For electrons, valence band for holes. So we have to do this integral. This integral can be rewritten by performing some manipulation in a symmetric way. I will not go through all of the details, but eventually you are left always with an integral over k of some integral which has this little singularity, this little pole. You can do lots of manipulation of this sort, and eventually you end up with an expression which has this form, assuming that the f that we have here is it's a pure exponential. So you are in a non-degenerate limit. Again, I'm pretty sure, but not totally sure, that if you don't make this assumption, you cannot solve this integration. If you have the Fermi-Dirac distribution function over here. This is where this exponential is coming from. I apologize for the notation. This beta now is the inverse temperature. It's not there's no suffix tf or dh, so it's 1 over kt. Okay, so you can do the integration by performing the integration regularly as we described before. It's a long procedure. At the end, you're left with, you see, this problem of having to deal with the singularities. The important thing is that at the end, you end up with a funny function, which is this integration over here, which is called the plasma dispersion function. I'm not sure why the word dispersion. I think it's because it comes when you try and calculate the dispersion relationship of classical plasmas in the classical plasma. But it pops out everywhere, since after all, we know that we're going to have to deal with plasmons and plasma response in terms of the dielectric, the dynamic response of the free carriers. Is not a surprise that you end up with this expression. So I think the plasma dispersion is a function of various variables. When you deal with, sorry, let me go back here. So the important thing is that at the end, so let's ignore that complicated algebra. You can do it with the Kramers-Koenig relationship. You can do the integration only in a non-degenerate limit, and then you find that your dielectric function has a real part, that's beta square, has a real part, which is given by this messy expression, is what we saw, the Debye-Huckel expression, not surprising, this is in a non-degenerate limit, times a prefactor and a difference between two plasma dispersion functions. It also has an imaginary part, which is the optical absorption of free carriers, if you wish. And this is our plasma dispersion function. And this I showed here what is the asymptotic behavior. Okay, and one can define a function G1, which is defined, I forget how it's defined, I should have written it down somewhere, which is a proportional to the plasma dispersion function. And the basic result, and that's the only thing that you should remember, is that if I do things a little beyond the long wavelength response by considering the exact integration of the linear expression, my Debye-Hückel or expression, again, we're in a non-degenerate situation, is modulated by a function, or here it is, the expression of this G1, is by a function that decays with Q. So your screening effects become smaller yet. There is already a b squared, beta squared divided by q squared in the expression for epsilon. But there is an additional decrease of the screening effects due to this x, which is just ql in the denominator. This is a weak response. So there are some corrections. In some cases, I've seen them applied to dealing with impurity scattering. The impurity limited mobility in some semiconductors is still an issue. It's still, if you go and look at tiny details, the gross features and quantitatively even in relatively satisfactory way, they are accounted for. But if you go and look at some details, there are still some little nagging details that don't quite fit. There are many physical reasons beyond the simple screening effects. I will not talk about much about, for example, other sum rules which apply to the various models for impurity scattering, but I will discuss them briefly. Okay, so I apologize for this complicated derivation. If you want to digest it, I understand that it's very hard to follow. Even in class, when I have a blackboard, I never go through all of these details. It's better to do it by reading what they are. So you have the slides, you can check how this derivation is done. By the way, it's a conventional derivation. I don't know if I say it, but it's you can find it in Fetter and Wallecka's book, in Mahan's many-body theories book. So it's a conventional derivation, again, only in a non-degenerate limit. And it's based on this Surkovsky-Plemelji theorem, I don't know how to pronounce it, that is commonly used. Okay, so I did not intend to give you all the details of this derivation. It's quite messy. There are some cases in which you can do things exactly. For example, in a degenerate limit, if you go to low temperature, 0, in practice 0, then you can actually do the integration. And that's because you realize that, let's go here, for example, you can chop the integration. This is an integral that can be done by hand when you chop the integration at the Fermi sphere, at the edge of the Fermi sphere. So in that case, you can do integration analytically, and you get some expression. It shows, for example, an expression that you can have that has both the Q dependence and the omega dependence, which is something that at finite temperature we cannot get in a degenerate limit. In the static limit, in particular, you have this correction, and you see that when Q goes to 0, you get a behavior which actually is not as severe as it's here. You have to take the limit of this logarithm, but it's a correction that you have in the degenerate limit to the conventional Thomas Fermi screening. I had some plots to tell you what the situation is. This is for silicon. What I show here is the full numerical integration. So general Fermi-Dirac expression for the occupations, and what you get instead with the Fetter-Wallecka calculations that I outlined before. You see that when the density of free electrons in silicon, the G is from where I got the plots from, is the density of electrons in a polysilicon gate, but it's just silicon. You see that there is a pretty good agreement between what you get in a high temperature limit, which is non-degenerate, and the full numerical calculations. By the way, these calculations are something that I did once, and I'm glad I don't have to do it again because it was a little painful. This is the room temperature for silicon, as I said. There is an imaginary part as well, and you see that they're pretty well reproduced. Okay. This is plotting the epsilon at the plasma frequency as a function of wavelength. This is plotting at the Debye length, or the Thomas Fermi, depending on what you have, or and the screening parameters as a function of frequency. Okay, you see the plasma peak, for example. If you increase the electron density, silicon becomes degenerate in the mid 10 to the 19, 3 times 10 to the 19 or so. So if you go beyond the degenerate situation, so you become degenerate now, you see that you begin to see some deviations. The plasma response changes, the frequency dependence and the wavelength dependence change quite a bit. Not dramatically, it's not a terrible situation, but it may matter. So it's not a completely satisfactory. So below, I would say 10 to the 19, you can use the Fetterman-Willek expression if you feel like tabulating your plasma dispersion functions. Again, let me show you the expression here. This. Otherwise, you have to go by with some more drastic approximations. So it's not an easy task. Let me conclude briefly. Again, I don't want to go into too many details. I put all of the slides that I had prepared, that I had in my notes, how to deal with the screening in 2 dimensions. I didn't deal with screening in 1 dimension. The 1-dimensional electron gas is a wasp nest because in principle it shouldn't exist. You cannot use a single particle approximation. A 1-dimensional electron gas actually becomes a Luttinger liquid, so it does not in practice, probably because the environment screens the Coulomb interactions. The differences between 3-dimensional and low-dimensional systems are mainly caused by the fact that screening is weaker. If you have a nanowire, for example, and you have 2 charges, opposite charges along the nanowire, most of the field lines that in 3D would propagate away from the direction connecting the 2 points, so they curve around, they would be in a medium, which has a high dielectric constant because of the static response of the valence electrons. If you have a nanowire in vacuum, those field lines go in vacuum, and they're not screened. So most of the interaction in 1 dimension is not screened. In 2D is not as bad because you have field lines that can propagate in the plane, but most of them propagate out of the plane, so screening is weaker yet. For example, we'll see that in the electrostatic quantum limits, so 1 subband occupied, screening does not increase with density. It's actually independent of density in the lowest order approximation. So screening is weaker. And in 1-dimensional systems, it's so weak, and the Coulomb interaction between carriers becomes so strong that it cannot be treated as a perturbation. And actually, the system collapses into a collective new quantum state, which is called Luttinger liquid. And in principle, one should see a different behavior. In practice, one never does. I assume because all 1-dimensional systems are surrounded by something that's supported by an insulator, some insulating substrate. They're embedded into the dielectric, and the screening that is resulting from the environment weakens the Coulomb interaction to such a point that the quantum liquid does not, the Luttinger liquid does not form anymore. That's my suspicion. Anyway, in 2 dimensions, things can be done in the same way that we did in 3D, with a little bit of a complication that in general, assuming that the perturbation that we have is in the plane, that is isotropic in the plane in which we are confined, in inversion layer, in a quantum well, for example. Usually, rather than using Fourier transform, one uses, I call it Fourier Bessel expansion. Sometimes I see that these are called Hankel transforms, whatever name you prefer. So essentially what you do is you go to polar coordinates and you express it in this term. You use block functions in 2 dimensions, of course, and they are, if we're assuming a silicon inversion layer of a quantum wells, we have subbands, and I've used Greek letters lambda mu nu that now do not label the bands of the crystal anymore. We're assuming to be in a single 3D band, but we have subbands. We can do exactly the same derivation that we did before in 3 dimensions, except that now we have this additional nuisance of the subband index. And then we have to consider the fact that our wave functions in the z direction perpendicular to the 2-dimensional electron gas are not plane waves, but they are confined. Zeta, the Greek letter zeta, is usually used to denote the z dependence of these wave functions that are plane waves in the plane of the inversion layer parallel to the interface between the semiconductor, the insulator, parallel to the plane in which the quantum well lies, but have a different dependence on the direction, on the coordinate along the direction perpendicular. The other nuisance that we have is now that you remember that in order to go from the perturbed wave functions to we get the charge, but if we go from the charge to the potential, we had to go through a Poisson equation. Now Poisson equation has different boundary conditions. Your inversion layer will be confined by an insulator on top. In a quantum well, you may have, say, indium gallium arsenide in the well, but aluminum gallium arsenide in the barrier materials. So the Poisson equation that you have to solve is messier. For the particular case of an interface, silicon-silicon dioxide interface, you can write the Fourier components of the Green's function of Poisson equation in this form. Please ask me questions. This is a little advanced, so I don't assume that you have ever seen this, but you understand that if I have a charge in a silicon inversion layer, there will be an image, which is exactly what this term represents, an image charge in the insulator, and this will affect the potential that the charge feels. So if I have a polarization charge, in order to extract the potential due to that charge, which is the polarization potential that I need to compute my dielectric function, I need to account for the presence of this charge. So this is essentially what one gets. It's convenient to use Fourier Bessel transforms in the plane and keep the coordinates, the regular coordinate z, perpendicular to the interface. So this is the effect of the charge, and this is the effect of its charge, which of course depends on what is the dielectric constant of the material. And these are the static dielectric constant that I'm considering here. So it's a little bit complicated now because we have matrix elements between various subbands. If I want to calculate the total charge, I have to sum over the subbands, and I have matrix elements over all subbands of this potential. You remember that before I had G vectors, I had the bands, I used my sum rule, and I said I can get rid of this thing simply, and I use just Fourier components. Here, unfortunately, I cannot do that because I cannot ignore inter-subband matrix elements. They matter. And so really, my dielectric function now becomes a tensor or a matrix, whatever you wish, and the matrix elements are between the subbands that I have. The simplest thing that people do is actually consider what's called the electrostatic quantum limit, in which you only have one subband. But in general, you have to deal with a more complicated expression and invert, going from the charge to the potential. You have to invert a matrix that connects the two. And so at the end, you end up with a very messy expression for your screening parameter. The screening parameter now depends on the subband indices, has a similar form that we had before, similar to the Lindert expression, which leads to the Thomas Fermi or the Bi-Huckel expressions, depending on what you do. Usually, you're degenerate in this limit when you're interested in, so it's a more complicated beast. But it's a similar expression, except that we had to drag along this complication of the many subbands and the fact that we also had to drag along the fact that electrons in various subbands interact in their interaction, there are overlap factors that you have to deal with. So just to give you an idea, there'll not be any questions in exams about this stuff, but it's more complicated, and usually people do some simplifications. So at the end, what you have to go to express the total potential from the external potential is not just a scalar. You really have to invert a matrix, take all the matrix elements between the subbands of the external potential, and you can extract the matrix element between all the subbands of the screen potential by applying the inverse of this dielectric matrix. Remember, this has nothing to do with the longitudinal response. This is different. So I don't even want to think about what happens if I consider the full dielectric tensor in the two-dimensional situation. It would be an awful problem. So the dielectric object, I don't know, it's this matrix, which actually is extremely complicated. People usually consider only diagonal terms, and usually you go in the extreme quantum limits, and this is what I want to show you here. If you take only diagonal terms, you get something which is very similar to what we obtained before in terms of the response. These are free carriers because they're in the inversion layer of quantum well, except that each subband contributes its own Debye-Hückel screening parameter in the same way that we saw before. And you can go to a single band, and you see actually that if you go to the Thomas Fermi expression that you have in the electrostatic quantum limit, in which you go to a single subband at a very low temperature, screening does not depend on the density anymore. This G mu is actually the degeneracy of each of the subbands. So very similar. The numbers actually will be different. Notice that there is a factor of 2 that we do not have in 3 dimensions, which already reduces screening. And screening in this expression actually does not increase with density. And that's because of the low dimensionality of the system. We can look also at plasma oscillations in the same way. The basic idea is that you have exactly the same expression that we had before, except that the plasma frequency now depends on Q. In particular, the plasma frequency depends on the square root of Q. Forget this factor, which simply says that the inversion layer has some extensions and the charge has some vertical distribution. We can ignore that, and typically people assume that your inversion layer or your quantum well is a delta function of 0 thickness in dealing with dielectric screening. But you see that the plasma frequency now goes to 0 as Q goes to 0, again because of the dimensionality of the system. And if you're close to the interface, things may change yet. You may actually go from a square root dependence on Q that you get from here to a linear dependence on Q because of the interaction of the plasma with its own image in a dielectric, which is nearby. So again, I'm not going to ask you in exams any of these things, but in 2 dimensions, there are some interesting differences with respect to what you have in bulk. Screening is weaker. Static or dynamic screening by the free carriers gets more complicated because you have many subbands, and all of these subbands contribute. And in principle, this expression that I wrote here accounts for the inter-subband polarizations, which in principle can induce a non-longitudinal component, which is ignored here. So as complicated as this might be, is not exact, is not fully correct. One would have to go to the tensor analysis. And you can derive some expressions for the non-degenerate case, which is seldom interesting in 2D, so this is just a curiosity. More important, and that's very important because it's used a lot, Frank Stern in the 1960s provided an expression for the dielectric function. I wrote here just the screening parameter here, analytically at 0 temperature. In its famous physical review letters, polarizability of the 2-dimensional electron gas, so that you can have the full wavelength and frequency dependence of the dielectric response at low temperature. This is in the electrostatic quantum limit, in which you have only one subband occupied, which is what happens at low temperature in a silicon inversion layer at very high gate bias, in which only the bottom subband is occupied. Okay, I will stop here and take a break. I need it for my voice. Shall we meet at about 1:45 to take a 10 minutes break? Then I want to give you some examples about simulations which have been done beyond the approximations for some two-dimensional, low-dimensional materials. And then I think, finally we'll be able to go into scattering of electrons. Okay, so any questions so far? Do I exist? My usual question. We have been online all the time. Yes? Okay, so let's take a 10 minutes break and then we'll go into the next topic. All right, are we all back? Can we resume? Yes, no? Am I online?
Yes, you're online.
My nightmare. I mean, at my age, you begin to talk to yourself anyway, but not for 3 hours in a row. Not about this boring stuff. All right, so let's resume. One thing that I want to show you is this dialectic thing. Uh, so we're all busy, and our main goal is to study field effect transistors or whatever. And nowadays, it has become mandatory to do atomistic simulations, right? If you don't do atomistic, you're not in a ball game. The issue that one has is you have interfaces, right? You have your two-dimensional material, you have your nanowire, and then you have an oxide. And eventually you do your transport, charge transport study, you get charges, and then you want to solve Poisson equation to get the self-consistent potential. And of course, the Poisson equation requires that you know epsilon, the dielectric constant function. Let's stick to the long wavelength static limit. Even in that case, it's interesting. So what do you do at the interface? You don't, usually when you use a continuum limit, you say this is silicon and below this particular horizontal line you have silicon dioxide. You mesh your system, and in one mesh element you have an epsilon, in the next mesh element another epsilon, and then you solve your Poisson equation correctly. But if you're using an atomistic calculation, where do you draw the line? This is something that it's hidden under the rug in many studies. So the idea is, can we calculate by using the random phase approximation? Can we, and some atomistic model, we used empirical pseudopotentials in this particular case. Can we calculate the potential without having to use a dielectric constant, so accounting explicitly for the polarization charges? Or in other way, having done that, we can extract a microscopic position-dependent dielectric constant. This is a term which is considered to be totally inappropriate by many physicists. There's no such a thing as a microscopic dielectric constant because you cannot define a polarization at one point. It's a non-local effect. Nevertheless, if you define it properly and you extract it properly, you can define an object like that. And I will show you some plots about this business. So what do you do? What we did, that was a student of mine, Jingtian Fang, who did it a few years ago now. What we did was, you remember that in a supercell that we described to use, you can use to simulate low dimensionality structure, you can add an external potential. Of course, invoking a fake periodicity of the potential. But what we did was, indeed, we consider a nanowire or a graphene sheet, for example, and applied an electric field, and then solved the Poisson equation self-consistently, accounting for all the polarization charges, considering the random phase approximation. So exactly the same expression that I showed you before for the dielectric susceptibility. And so you can essentially solve a Poisson equation with the polarization charges that implicitly accounts for whatever is the dielectric response, electronic only in this case, of course. So that's what we did. In this case, you don't even have to use many of the approximations that we used before. Perturbation theory, yes, in this case, because we're perturbing the wave function. We toyed with the idea of actually solving self-consistently and using the perturbed wave function, taking the difference. It's something that you can do. You don't have to consider the longitudinal response only. You can consider also the full dielectric tensor, and I will show you indeed some results about the off-diagonal response that you do have in some cases. So this is something that can solve this problem. Unfortunately, we haven't gone as far as implementing it into a simulation model, but it's something that we have in mind. So for example, for graphene, what I show here is the polarization charge that we have. This is the total potential, and this is the induced charge that you have. So the potential goes from high to low, and you see that you induce some charges. The little crosses are the atoms, the carbon atoms. And you see that the wave functions indeed is polarized, and you see what you can extract in this way by using some way to extract a position-dependent dielectric function. You see that indeed you get vacuum, one, outside far away from the graphene, and then you reach a peak in the center of the graphene sheet and you go down. Notice one interesting thing. You don't quite get to the value that you get for graphite. The reason is that when a material is embedded into some medium, in this case it's vacuum, the polarization tends to follow or approach what the medium, surrounding medium does. So if you have a medium that doesn't polarize at all, like vacuum, the polarization of the graphene is reduced quite significantly. If the polarization of the material surrounding the medium, the graphene sheet is very high, say you had hafnium oxide, I would expect that instead the dielectric function that you see in the middle of the graphene sheet would be very high, except that it would be probably a curve which is flipped. You would have your 24 or whatever it is for hafnium oxide, then it would drop to some value bigger than 6, which is the value that you would expect in bulk, and for graphite, and then it would go again to 24 in a substrate. So it's an interesting thing when you have a very tiny nanostructure which is embedded in an environment. The environment affects the not just the dielectric properties, the entire electronic properties of the system. We know that it can change the band structure to some extent, and definitely it affects electron-phonon interactions and all interactions with the dielectric response of the medium itself. So this is one example in which what we call the environment, the dielectric environment, really is extremely important now that we go to structures which are of the nanometer or even sub-nanometer scale in some cases. This is a armchair edge graphene nanoribbons. We discussed them in the past, how interesting they are in terms of their claromatic behavior and so on. And here you see the various components of the dielectric tensor. These are the diagonal components, and these are the off-diagonal components. This is the usual one that you would consider, the out-of-plane. This is the in-plane, and these are the cross terms that you have. So although this is a parallel plate capacitor with the plates up and down, still you have some polarizations in a direction which is perpendicular to the field that you apply. In this case, you see that you have a dielectric constant which approaches the one that you would get for graphene in this particular case for graphite, but then you have some spikes in the epsilon at the border because you have an additional surface. I wouldn't call it surface for this monolayer, but whatever. At the bottom and top of the layer, you have some additional polarization. And depending on the width of the nanoribbon, you see that there are some differences that, of course, are related to the claromatic behavior of the ribbon. For we study also graphene on HBN, and the 3x3 atoms silicon nanowire. And you see again that for the nanowire in vacuum, the dielectric constant that you get in the middle of the wire is very small, much smaller than 11.7 or 11.9, whatever you prefer. So this is just the longitudinal component of epsilon. And you see that we get a value which is about a third, less than a third of what we would expect. Excuse me. Again, because of the vacuum around this medium is essentially reducing the polarizability of your tiny wire. I don't remember if we studied the situation in which the dimension of the wire increased. At the time, we didn't have a very numerically efficient way to deal with very large structure. Now we do. We could study probably the same effects in a bigger wire. I expect that when the wire gets bigger and bigger, the dielectric constant in the middle of the wire begins to approach that of bulk silicon. Okay, so this concludes this dielectric, the discussion about the dielectric response of a system. Again, we will to revisit it and use it in dealing with electron scattering with various perturbations. So I think late last week I posted some slides about this today's lecture. I usually prepare lectures far in advance, so at the time I thought that I would talk about superconductivity because it's phonon related, and we've talked about phonons a little bit to give you a flavor. Superconductivity now is becoming very interesting also from a computing application because of quantum computing. Among the various ideas that people have for the building blocks of the quantum computer, which are the qubits, superconducting Josephson junctions are considered one possibility. It's not easy because you have to preserve the entanglement of the systems and so on. Other candidates are, I think, even more far-fetched, like cold ions, although there are some interesting results about that. Another thing is quantum dots. The reproducibility of those things is a tricky business. So Josephson junction is probably the most interesting. So to give you an idea about superconductivity related to two-dimensional materials, I decided to postpone it until we will have discussed the electron-phonon interaction so that we can go into some detail, not too much, about what we expect to be the role of superconductivity, the phonons in superconductivity. High temperature superconductors, we don't even know whether phonons are involved or not. There is a diatribe in the literature. We're still missing a definite theory about them. Many proposals, but many of them involve phonons. The fact, for example, that there are isotopic effects seems to indicate that phonons may play a role, but not everybody agrees. So before doing that, let's go to one of the core of the class, which is electron scattering in solids. By solids, I remind you that I conform to the nomenclature that Sir Neville Mott gave. A solid is a crystal. If something is not a crystal, it's not a solid. So an amorphous material is supposed to be a liquid. It's only a matter of temperature. So replace crystals if you wish in the title of this slide. So we will talk about, first, the generalities about scattering in semiconductors. We will use Fermi-Golden rule, essentially because that's all we know how to do. Dealing with interactions that require something beyond perturbation theory at the leading order is extremely difficult. Actually, superconductivity is one of the few examples that we have about theories that go beyond perturbation theory simply because some collective quantum states like Cooper pairs, like fractional quantum Hall effects. I think if I have another example in mind, those are typical examples of theories that cannot be reached by perturbation theory. There's no expansion, power expansion for example, the critical temperatures. It depends on a negative of an exponential of 1 over the effective potential that cannot be expanded in power series of the potential. So, but in general, that's all we know how to do. We'll use Fermi-Golden rule, but there will be some complications because we have block functions rather than plane waves. So we've had to, first of all, establish rigorously the machinery that we will use to describe the scattering rates used, even if only using Fermi-Golden rule. Then we'll go into examples, important examples. The electron-phonon interaction, of course, it's unavoidable. Even at very low temperature, phonons can be emitted by electrons with a sufficiently high energy. Actually, even acoustic phonons, there is a threshold which is the equivalent to the Cherenkov effect. So the electrons have to have a minimum energy to emit phonons, acoustic phonons, but they can, above some crucial velocity, which is the acoustic velocity. We will deal with scattering with ionized impurities, interaction with free carriers, and finally we look at interaction of light with matter, so radiative processes. So these are the main interaction. I will add a few odds and ends here and there about some complications, like for example, the interactions, my clock now, the interaction of electrons with interfacial modes which result from the coupling of optical phonons and plasmons in polar materials. Scattering with ionized impurities is another wasp nest, and this is even more complicated. So bear with me, and we'll go slowly, ask questions when things get confusing. Okay, lots of talks that I got from here. So we're going to use Fermi-Golden rule. So the idea that it's in this slide is, so far we've dealt with ideal crystals at 0 temperature, look at their band structure. Then we've looked at the ionic component of the Hamiltonian and look at what happens at for small excitations of the system, the vibrionic or vibrational degrees of freedom, phonons, the collective excitation of electrons, plasmons. These are small excitation above the ground state. We have not touched the electronic Hamiltonian at all. Now we have to go there and say, yes, in the electron Hamiltonian, we consider the ions to be fixed at their equilibrium position. We have considered all of the other electrons to be in their equilibrium state, screening that we've just dealt with. What happens if we go off equilibrium? What happens if there are perturbations of the system which arise from excitations of the system itself, like thermally excited phonons, that modify the term of the ionic potential felt by the electrons? Similarly, for the electron-electron interaction, we have looked at a mean field approximation, Hartree and Hartree-Fock, but there'll be fluctuations around this state, which will give rise to Coulomb interactions among electrons. What about deviations from ideality of the system itself, like the dopants that we introduce, ionized impurities, or defects that might be present? We will not discuss those, but they may be present, they may be charged, they may be neutral, but they will contribute to perturbing locally the band structure, the crystal structure, so the band structure, and they will act as scattering centers. So there will be perturbation of the system. So we will use Fermi-Golden rule. So we have some perturbation Hamiltonian H prime, which in principle is function of position and time. I write HQ, as usual, I forget the omega here, we will deal with it separately, and we consider one in a linear response approximation that we use also for scattering. We consider one Fourier component at the time and see how the system, the electrons respond. And then we use Fermi-Golden rule and say, okay, the rate at which an electron in band N with crystal momentum or wave vector k scatters with per unit time with this perturbation is given by the square of the matrix element between the initial electron state and a final electron state. Energy is conserved. This is the same delta function that we just saw from the Kramers-Kronig relationship, coming from the fact that I showed you where Fermi-Golden rule comes from. And then we sum over all possible states that conserve energy, thanks to this delta function. We know how to deal with him in free space. This will be just the Fourier component of the Hamiltonian H prime, so it will be an H of K prime minus K instead of Q over here. The problem that we have is that now these states are not plane waves. Yes, there is a plane wave, but there is also the periodic component of the block function, which is the remnant of the atomic orbitals, as I said. Here I've written V for the volume, which is thinking of finite volume normalization. We will usually go always to infinite volume normalization, so this sum over K, it should be 1 over V, will become an integral over all K space divided by 2 pi cube. So we can represent the block function in this way by explicitly taking the Fourier components of the periodic component, of the periodic part of the block function, which of course has only terms which are non-zero when the Fourier component is at a wave vector, the reciprocal lattice. So we have to calculate now this messy matrix element between these messy wave functions. So we can just plug in this expression for nk, the complex conjugate of this for n prime k prime, just replacing k with k prime and considering a band n prime, which is over here. And then we have this expression. This e to the I qr hq comes from having used the Fourier expansion of the interaction Hamiltonian. These are coming from these objects. These are coming from, these are just the Fourier components written this way, which I later on will expand into this form, but not now. And so the matrix element is given in this form. It's convenient to express the variable r here, splitting. I'm integrating over the entire space. What am I doing here? I apologize. Okay, and I lost the PowerPoint there. Okay, and so it's convenient to write r as, instead of an integral of the entire space, as a sum over cells and then an integral over each cell. So the translation vector RL is taken outside, this exponential over the RL is outside, and inside I have this row, and this row is a coordinate that spans a single cell. And that's because I want to use essentially the periodicity of the system to express everything in terms of what happens inside a single cell. Okay, so the sum over L of this object, we know what it is. Okay, this is just the delta function. Of course, sum over all possible G vectors. This is something that we've seen before. It says page 117. You can go and look in the notes, but it's early on. I think when we derived the effective of equivalent Hamiltonian expression for the single electron Schrödinger equation in the presence of the slowly varying potential. So we can rewrite this matrix element as a sum over G. Now I'm using the delta function to express these objects because it's a delta function. So I can replace with the k minus k prime plus k plus G, which is what I've done here. And then I have an integral over a single cell of this object. And I can write it as a sum over bands, because of n prime. It should be a sum over n prime here. Sorry, there's no sum over n prime here. I'm just fixing n prime. I will do it later in the Fermi-Golden rule. So it's just the Fourier component of the Hamiltonian as I would have in free space, except that I have this annoying sum over G vectors because of the periodicity of the crystal, the form of the block function. And then I have what I call an overlap integral. It's the Fourier components of an integral, if you wish, this depends on G as well, of the periodic components of the block function. So basically what I have is, if I take this expression and plug it back into Fermi-Golden rule, I have the usual expression that I have in free space, except that I have this cumbersome sum over G, and instead of having just a delta function expressing momentum conservation, now I have a fuzzier object here, which is given by the how much the initial and the final states overlap in terms of their atomic orbitals, if you wish, of the various k points. So very similar, except that I have this object. Okay, in practice, in most cases, what happens is the Hamiltonian decays with Q. In most cases, not in one of the most important one, which is scattering, non-polar scattering with phonons. But every Coulomb interaction has a matrix element which has in the denominator the momentum transfer, which is this object. So usually the G's are big. So if I have a matrix element which has this in the denominator, the magnitude of this vector in the denominator, often elevated to some power, usually even the shortest G vector, different from zero, will give a contribution which will be much smaller than the leading term, which is the G equals zero. The G equals zero processes are called normal components. The process in which G is not zero, they're processes in which an electron is scattered to a vector K prime, a position K prime, which is outside the first Brillouin zone, and then I bring it back into the Brillouin zone. And this is called an Umklapp process. Umklapp in German means folding over. So that's what you do. You essentially, when you consider the extended zone scheme and go to the Brillouin zone, reduced zone scheme, you fold the band structure over the first Brillouin zone. So this is why it's called Umklapp. And in addition, this term, if we're dealing with electrons which are not very far away from the minimum of the conduction band, for inter-valley processes, so say gallium arsenide around the gamma point, usually if you look at the mobility, for example, only a very small region of K-space is probed because of the Fermi Dirac occupation of the electrons, not too far away from thermal equilibrium. So K and K prime are not too different. So this two-wave function, this periodic component of the block function, are not too different. If I stick to the single band, these are essentially the same. For different bands, they would be almost orthogonal. So you only have on intraband processes, that, by the way, energy conservation usually implies that. And this is not too different from one. So in many cases, this is set to one. Inter-valley processes, they can have an overlap factor. The square of this object can be significantly smaller than one. I think for silicon, for the F and G processes, which are the scattering between the various ellipsoids, the 6 ellipsoids, they can be as small as 0.7, 0.6, something like that, depending on K and K prime. Again, one important thing that I have to remind you again is we can ignore this thing in most cases, set this to 1 and be done with it, maybe lump this factor, which is smaller than 1, into some parameters that we have, like a deformation potential over here. But we cannot do that in optical transitions because we really need to know the angular momentum of these functions, because optical transitions involve only states that have a total angular momentum that differs by 1, plus or minus 1. So in general, this will be simplified to 1, and only normal processes will be considered. Scattering with acoustic phonons is different because it actually, the matrix element grows with Q. So Umklapp processes are important. Another example in which Umklapp processes are extremely important is heat conduction for the phonon-phonon interaction. Okay, so this is what I say here. Typically, we'll consider the overlap integral roughly equals to 1, order 1. If you want to be quantitative, we have to be, of course, careful about it. And we will treat separately contributions between the normal and the Umklapp processes. So this is a general scheme in which we have to work on. So Fermi golden rule, again, but a little bit of a complication because this matrix element is different. And of course, the density of states that control scattering is very important. Notice indeed that scattering depends on how many states you have at a given energy. There is a typical analogy that I have why the density of states controls scattering so much. It's related to parallel parking. For student drivers, it's a major issue to park a car in a tight spot in parallel parking. It usually takes much longer to get in a parking spot than get out. And that is a density of final states effect. If the density of final state is small, when you park the car, You don't want to be too close to the car in front, to the car on the back. You don't want to be too far from the curb, from the sidewalk. Otherwise, you damage your tires, or you're too far in the middle of the road. So you're really limited to a small region of real space. Density of states are small. When you want to get out, you can be way sloppier. So the parking rate is much larger when the density of final states is large when you get out of the parking spot than when you want to park the car. You have a small scattering rate because the density of final states of your car will be smaller. Same for electrons. Electrons will scatter more when they can choose between many states which you can go to. Instead, if the density of state is small, they scatter less. So typically, this term will be responsible for a term which will increase with energy. In some simple model of parabolic bands, it will increase with the square root of energy. Then, of course, if you go to a full band structure, it will decrease as the conduction band disappears and dies. But in general, this will be proportional to the density of states. This matrix element, excuse me, will give a significant contribution, especially for Coulomb interactions. This will actually decrease with energy. So at the end, you may end up with a scattering rate which drops in energy. Coulomb interactions in general decrease in energy, and that's easy to understand. An electron that is bound in a crystal sees a potential in a crystal which is of the order of 10, 13 electron volts, a Rydberg. This is the typical energy we're dealing with. An electron which has an energy of 1 volt clearly will see any perturbation as extremely important. The presence of the crystal extremely important. An impurity over there will have a depth of the potential which will be within the screening length. It will be of the order of a few electron volts. Big, but not tremendously big. But if the electron has a thermal energy, of course, this will be a huge potential. If the electron has an energy of a mega electron volts, who cares? It will not even see the crystal. And that's why Coulomb interactions at high energy gets weaker and weaker as the energy increases. Okay, so this is the discussion that I told you. I will also have to make a difference between static perturbation, in which this is zero, impurity scattering, for example. Impurity sits there. Okay, you may go and say that it may vibrate a little. Yes, that would be a localized phonon, for example, but typically we can ignore it. From dynamic perturbation, and dynamic perturbation will be mainly phonons, interaction with other electrons, in which you have an exchange of energy. A general characteristic that we will see later on is that interactions of electrons with scatterers that do not have an internal degree of freedom, like an ionized impurity, when we ignore its vibrations and we ignore possible excitations between the various states in impurity. This is just a static object sitting there, no degrees of freedom. The interactions will be fully reversible in time. Interactions with excitations that have internal degrees of freedom, like phonons, they are degrees of freedom of the crystal. They will usually always be non-reversible in time, irreversible. Okay, electron-phonon interaction. Let me start with giving a broad outline of the various types of interactions that we have. Interaction, the electrons can interact with phonons in two major different ways. One is a non-polar interaction, and it's convenient if I introduce immediately here the concept of a deformation potential. So what is a phonon, an acoustic phonon, or even an optical phonon in a non-polar material? There's no electric field associated with that, per se. There is a distortion of the Coulomb interactions in a crystal because the ions move away from their equilibrium position. But there's no long-range electric field, dipole field. Instead, what the electron sees is when a phonon comes by and the ions move with respect to one another, it sees a local change of the strain, which is applied to the crystal. It can be a complicated strain. It can be a dilatation strain. mainly a longitudinal acoustic phonon in one direction is a dilatation. Because of the elasticity theory, a dilatation in one direction implies a compression in the other directions. Well, the ratio of the displacements is called the Poisson ratio. And so you have a rather complicated biaxial strain or uniaxial strain locally. A transverse phonon may have a shear component, some mixed mode in some mixed direction, not principal direction of the lattice, may have some torsion, which is essentially a shear distortion. So the strain may be complicated, but every type of strain that we apply to the crystal introduces a distortion of the band structure. In particular, if you're dealing with electrons, the bottom of the conduction band, which is where we're interested in right now, will move up and down. So if a phonon comes by and electrons localized around the wave function of the phonon, we'll see a change, a dynamic change, an oscillation of the bottom of the band structure, of the conduction band, as the band structure changes dynamically. The term deformation potential is used usually for what you see as a deformation of the changes of the band structure when you apply external stress. Of course, stress can be of various types. As I said, can be dilatation, which is hydrostatic, can be strain, can be shear, can be uniaxial, biaxial, whatever. Elasticity theory can be used to sort out all of these strain effects. But the idea that originally Bardeen and Shockley had in 1950 was, at the time, it was almost impossible to calculate the electron-phonon interaction, the matrix elements. Now we can, with caveats that I may have to discuss later on. But we can. At the time, it was unfathomable from a numerical complication perspective at the hardware situation. So what they said, well, can I relate the change of the band structure that people measure in a lab when they apply stress to a crystal to the mobility that I see in materials, in non-polar materials, in which the mobility is limited by interaction of this short-range type of the strain. And this is the deformation potential theorem, if you wish, in which you can relate with caution what people measure in a lab with, say, hydrostatic pressure, for example, or various biaxial and uniaxial strain in crystals to the mobility that you see. With cautions, because there are effects like this guy that it's not accounted for in this deformation potential theorem. Intervalley processes, which are not accounted for, not to mention scattering of various types, like long-range scattering. So in some situations, this is extremely powerful. Ironically, if you look back at the paper, they estimate the deformation potential for the electron-acoustic phonon interaction in silicon by looking, I think that they consider the intrinsic mobility in undoped ideal silicon to be something like 300 centimeters square per second. That gives you an idea about the quality of the crystals at the time. It's about a factor of 5 smaller than what we know it is in good silicon. Early days. This was the year after the invention of the transistor, right? So I'm not sure that silicon was of much interest yet. It was all germanium up to that point. Okay, so this is the first type of interaction. Optical phonons do the same thing. They also distort the band structure. And so there will be a non-polar interaction between electrons and phonons. And this is what we call the deformation potential or Harrison interaction. Harrison in 1956 published an extension of the Bardeen-Shockley theory. The nonpolar interaction is valid, is effective in all materials. And again, it can be with acoustic and optical phonons. So I created a small matrix to remember what we're talking about. So these are present in all materials, polar and nonpolar. In polar material, there are additional scattering processes, and that's why maybe, say in gallium arsenide, scattering with acoustic phonon is not the dominant process. It matters, but other types of interactions matter more. because the material is ionic, and so there is a long-range interaction. Optical phonons create, of course, a dipole field, which is a longer-range interaction. So the difference is that the short range is proportional to the lattice displacement, the local displacement of the ions, and this is proportional to the wave vector. It gets stronger as the wavelength gets longer. Instead, shorter, sorry. Instead, polar interactions are coulombic, and Coulomb-like interactions, as I told you, have some Q in the denominator. I wrote 1 over Q, it can be 1 over Q squared, depending on the dimensionality, depending on what it is. And this is for the potential, not the square potential that enters the interaction. So this is roughly qualitative behavior. So the polar interaction decrease in strength at short wavelengths, the non-polar interaction instead increase, okay? So it's a completely different behavior. So you expect that this will lead to interaction with increase as the electron energy increases, in addition to the density of states. In the opposite, as I said before, this interaction will decrease in strength as the electron energy increases. Optical phonons generate a dipole field, and Froelich, it took me a while actually to find the correct reference, because I noticed that in the literature they give a reference to a 1935-34 paper in the Proceeding in the Royal Society of England. This is not, I looked at the paper finally, and it's not there. The real definition of the Froelich interaction was given in 1954. From what I could see, I couldn't get this book from 1949 that is referenced in this paper. And that's where the expression for what we call the Froelich interaction is. The 1935 paper is actually on the electric breakdown in dielectrics and in insulators, but it doesn't deal with explicitly with the expression that we call Froelich interaction nowadays. Although it's hinted, but the expression is a little later. So we're talking 1950s about where these things came from. Now, acoustic phonons also can generate a long-range field. I guess most of you have an example of one such process at your wrist. The quartz vibrator, the oscillator that vibrates and oscillates and gives you the clock for your watch. That is usually a silicon dioxide, a quartz crystal. A quartz is a piezoelectric material. Piezoelectric means if I squeeze it, I generate an electric field, and vice versa. If I apply an electric field, the lattice distorts. And indeed, the oscillation comes out of the interaction between these two things. You apply an electric field, the crystal begins to oscillate, and this gives an oscillating field, and the eigenfrequency depends, so the frequency at which this oscillation occurs depends on the shape, size, and so on of the crystal. And that's what calibrates your watch. So I couldn't find a reference for the original paper that describes piezoelectric interaction between electrons and acoustic phonons. But keep in mind that in some materials, also acoustic phonons can interact with electrons. In polar materials, clearly. Silicon is germanium, diamond, they are non-polar, so they don't have piezoelectricity. But gallium arsenide does, as does silicon dioxide, hafnium oxide, and so on. With a few exceptions that have been discovered recently, piezoelectric scattering matters only at low temperature. At room temperature, you can ignore it. We will not discuss it. There are some exceptions. For example, two-dimensional selenides seem to have a strong piezoelectric scattering with electrons. So the polar long-range scattering with acoustic phonons is significant in these materials. But they are pathological cases. Well, I don't know. Recently, selenides have received a lot of attention, especially from TSMC. I just saw a paper which they deal a lot with selenides. They actually asked us to study them. They may have some promises in terms of transport properties, growth, stability, and compatibility with silicon technology, and that makes them interesting. So In nonpolar materials, these are the main processes, especially scattering with acoustic phonons. In polar materials, these are the main, this guy, the Froelich interaction, which is the interaction of electrons with optical phonons, dominates. I remind you, longitudinal optical phonons only. We talked about it last time. I reminded you an hour and a half ago. Electrons can interact via Coulomb interactions only with longitudinal excitations of the system. So the electrons do not interact via polar interactions with transverse optical phonons. Ideally, then of course, phonons are mixed and the usual story. So there are deviations from ideality. So how are we going to deal with the electron-phonon interaction? Half an hour and I can go through at least the basic concepts. So I remind you that we looked at the electronic Hamiltonian. This is something that we dealt with as a first example of second quantization. We write a Hamiltonian density, or a Lagrangian density if we put a plus here, which is such that the Euler-Lagrange equation, which gives the Lagrange principle of minimizing the action, which is the integral of the Lagrange over time, gives us a Schrödinger equation, which we look at as a classical equation for a classical field psi. Quantizing it, the field psi and its canonically conjugated momentum density pi, so I should put a hat over here when I quantize it, they become operators over a Fock space, and I can write the electron Hamiltonian in this form. It's a collection of harmonic oscillators. Each oscillator has a frequency which is given by the energy of an electron wave vector k in band n, and these are the creation and annihilation operators for those electrons. Notice that this operator satisfies the canonical anti-commutation rules because we know that electrons are fermions and they must obey Pauli's principle. My logic is upside down, but you know what I mean. Pauli's principle follows from the canonical anti-commutation rules, and we know that from the spin statistics theorem. That's the correct logic. Okay. For phonons, we did a similar thing. We wrote the Hamiltonian of the phonons in terms of their kinetic energy, their potential energy, by using the harmonic approximation, by taking only the leading term in the Taylor expansion of the interionic potential. The first derivative, I remind you, is not zero, but if I sum over all the ions in the lattice, L denotes the cell, gamma denotes the ion in each cell. If I sum over all of the forces acting on each ion, clearly I get zero at equilibrium, which is what this zero means here. And if it weren't zero, then I would not be equilibrium. The ion would move to another position, the equilibrium position. So the leading term is the second order term, third order terms, and fourth order terms, and so on. They're anharmonic terms which express phonon-phonon interaction, phonon decay. And for now, we'll ignore them. Actually, we'll ignore them forever in this class. I will not deal with phonon-phonon interaction. So we could do the usual things. It was not so obvious, but we wrote this. It's a function of a p square and an r square, roughly speaking. So it looks like the Hamiltonian harmonic oscillator. We find the eigenmodes of the system by using the periodicity of the lattice, expressing these variables in their Fourier components. Each Fourier component does not depend on a cell, so we reduce the problem into solving the eigenmodes of a single cell, and we got 3n modes, where n is the number of ions in the cell, 3 acoustics, 1 longitudinal, 2 transverse, and the remaining 3 times n minus 1 optical modes. For diatomic materials with 2 atoms per unit cell, it will be 3 acoustic and 3 optical. And we quantize them, and we managed to write it in terms of creation and annihilation operator of an eigenmode, a phonon, of polarization eta. This labels the branch. Let's call it polarization, but it's really a branch. Transverse acoustic, longitudinal acoustic, transverse optical, longitudinal optical. This is what eta labels. Q, the wave vector, and then the frequency of the harmonic oscillator, and this is the phonon dispersion that you find by solving the secular equation for the dynamic matrix, which is the lattice Fourier transform of this object. Okay, this is what we've done in the past. Now, the difference is that we have to go back to the electronic Hamiltonian and say, boy, this V, this is the sum of over all of the ions in the crystal of the ionic interaction between the electrons that are at the ion L gamma, not at equilibrium anymore. We consider it at equilibrium when dealing with this thing, but now we have to account for the fact that the R can move, it becomes a delta R, which is given by the presence of a phonon. So the interaction, the perturbation that we now have to consider will be the sum for each electron at R. It will be the sum over all ions in each cell, over each cell, of the change of, to first order, the gradient of the potential, the interaction between the electron and the ion L gamma, multiplied by the displacement of the ion. If we plug this in here, now we get a term which will be an integral over R. Remember that this is psi dagger, so it will be psi dagger psi, which is essentially psi star psi, which is the electronic density, multiplied by the potential. If I multiply by E, I get a charge times the potential, which is the interaction energy. So how we do consider that? Well, we second quantize it by looking at what delta R is at the ion L in cell L in position gamma in the presence of a phonon. And you remember that we found an expression for this, an explicit expression. And this, well, we have to deal with it somehow. We have to find some expression for what this potential may be. It may be the pseudo-potential. It may be a self-consistent or empirical pseudo-potential. It is some empirical parameter that we may fit to data if we don't want to do any ab initio calculation. So not be predictive, but post-dictive, which is usually easier than predict. Okay, so what we're going to do is we will write this in terms of what delta R is, and the delta R, so we sum over L and gamma, which is what we have here. Then I've written the delta R in terms of his second quantized expression, if you want. This is the polarization vector of a phonon of branch eta, and wave vector Q for an ion gamma. Remember, this does not depend on which cell I'm in. The dependence on the cell is all lumped into this exponential term. It's a wave, and this is where the translation vector of cell L comes in. This is the canonical coordinate that I used that we express in terms of creation and annihilation operators. Okay, so this is the full, in its full glory, the expression that I have. This factor is, you remember, I stressed it more than once, it is the scale of the system. It is the magnitude of the displacement of ion L gamma in the presence of a phonon with momentum Q at branch eta. And this is what comes out from the canonical commutation rules of the BMB dagger. So that's the importance of those canonical commutation rules. They tell us the strength of the interaction between electrons and phonons, among other things. So not a trivial consequence of that. So now what we do is whatever this V gamma is that we take, again, empirical and self-consistent pseudo-potential, some purely empirical form, whatever we can find, it has to be periodic, so, and has to have this form, so we can expand it in Fourier transform, okay? So I actually have replaced this term, one of these things, the tau gamma. The tau gamma, remind you, is the position of ion gamma in a given cell. It's the same everywhere because of periodicity of ion gamma, measured from the reference point of the cell, the origin of the cell. And I've lumped it into this expression, okay? So we get that the gradient would be proportional to K. And that's where the dependence of Q that I told you before is coming from the fact that I'm looking at the gradient of the displacement. So the electron phonon Hamiltonian now is given by this. Again, all I've done is add a delta V in here, reminding you that 1 over h bar psi, pi is equal to psi dagger with an I that we'll ignore. So this is the expression of the the perturbation Hamiltonian that we're dealing with now. Okay. What do we do now? We have second quantized the phonons, the delta R, written here, and we found it in terms of the creation-annihilation operators. Now what we have to do is plug in the second quantized form for the electrons. Why am I going through this thing? Why don't I use conventional quantum mechanics? For one main reason, phonons can be absorbed and emitted. I told you that conventional quantum mechanics cannot deal with a variable number of particles. Once you fix it at the beginning, you're stuck with it. Instead, we need to create and annihilate phonons. The result of this will be the derivation of the Einstein coefficient, spontaneous emission mainly. I talked about at the beginning, introducing the concept of second quantization in terms of electrodynamics. Spontaneous emission of photons for phonons is the same algebraic machinery because they're bosons. These operators satisfy the canonical commutation rules. So if I now plug this into here using for DVR this mess, okay, you realize that I have lots of e to the I kr, e to the I qr, kr over here, kappa r over here. They go away by becoming delta functions when I integrate over the entire space. So you get a, I'm hesitant to use the term, a simpler form, so to speak. This is actually quite daunting, but of what the electron-phonon interaction looks like. It's a mess, right? Here, I hope that you realize that this is something that has to do with the overlap integral, something similar to that script I that we introduced in the past by dealing with generalities of the electron-phonon interaction. Here we have the strength of the atomic displacement. So the strength of the electron-phonon interaction clearly scales with how much each ion moves around. The more they move from equilibrium, the stronger the interaction. This term comes because we're dealing with the displacement, with the gradient, so the displacement of the ions. If all of the ions are displaced uniformly, this goes to zero and we get no interaction. There's no relative displacement of one ion in one cell with the next cell, so there's no interaction. This is just something that depends on where the type of strain is. What is the polarization? Are we talking about a dilational wave, a shear wave, a torsional wave, a flexural mode, whatever it is? This is the type of strain, biaxial, uniaxial, that we're dealing with. It's a polarization vector. In which direction does each ion move? And clearly that depends on the strain that we have. Then we have something that depends on the periodicity of the crystal. This we said already, it's a scale factor that comes from the canonical commutation rules of the phonons. This is the interesting part. Notice what this does, this piece over here. That we'll describe it in the next slide. I have still a few minutes to talk, so let's go to the next slide. We can simplify this royal mess. It's not so simple, as I said, it's quite complicated, by doing the usual trick. This sum over here, if I pick this guy, this e to the I kappa RL and Q, I can lump it into the sum over L gamma, and I get the usual things. I get a delta function of Q minus kappa plus G. This is momentum conservation for the phonons. It says that the Fourier component of the potential that enters the picture is exactly what you get from the displacement of the ion. And then, of course, you have this complication of the periodicity of the crystal and G vectors. So unless you have this relationship, unless this is equals to G, then the process becomes zero. So you can simplify a little bit the notation by the usual scale factor. I'm summing over all the K, the Q, the G's, and so on. And then I have an interaction that depends on the gradient of the ionic potential, an overlap factor, that is the same factor we discussed before. And then there is this term, which is the dot product of the displacement, the Q vector of the phonon, in which direction does the phonon propagate, dotted with its polarization, which again labels the type of strain that we're dealing with. And then this important term. We can lump and define this entire object as script AQ, which is the coupling constant between the electron and the phonon with momentum Q and branch eta. So my electron phonon Hamiltonian now can be written this way. Notice, if I may use a sketch. Oops, wrong. No, it's a pointer option. Pen. Let's use a sketch, which is actually has a name. The sketch that I'm going to draw has a name. Where am I here? So I have an electron with momentum K, which is coming in. If I look at the possible matrix element of this electron phonon Hamiltonian that I have here, the only ones that will not vanish are those for which I have an electron at wave vector K. Forget the band index. I've deleted it here, but I must have an electron occupying the state K of an excited state of the harmonic oscillator corresponding to an electron at wave vector K. If I don't, I will have a vacuum state for that electron, and the annihilation operator acting on a vacuum state gives me 0. So I must have an electron with momentum K. Similarly, this term here must imply that I must have an electron with momentum K plus Q at the end as a final state. So if I go back here, I must have an electron with momentum K plus Q as a final state. If I look at this, I can't see my pointer when I use the pen. If this C, here I am, if this C acts on the left, then it creates on a vacuum state of an electron which is not there, Pauli exclusion principle, the state must be available. It creates one. If you wish, if you look at it acting on the right, sorry, the other way, on the left, then it must act on an electron which is already there. So the final state is an electron momentum K plus Q. The initial electron has momentum K. I talked about momentum is really wave vector. The crystal momentum will be h bar K and h bar K plus Q. And then what I have is an object here, a phonon, which is either created or annihilated depending on which I have. So it can go back and forth either way. And so this depicts this term represents, if you want, this little sketch I draw has a very clear mathematical meaning. If I draw an A over here, A of Q, this is exactly what this sketch draws, represents. It's a vertex, which is the strength of the interaction. An electron comes in, it is destroyed by the Hamiltonian and replaced with a Hamiltonian with momentum K plus Q. The momentum, the crystal lattice momentum Q, is given, taken or absorbed by the creation or annihilation. In this case, the B dagger will be a creation, so it will be a phonon emission, or an annihilation, a phonon absorption of a phonon momentum Q and branch eta. So there is a very clear, I hope it's a clear representation or intuitive meaning of what this particular term means. By the way, depending on how you view them, these are called Feynman diagrams. If you view this as time, these are called Goldstone diagram, but essentially they are a quick way to represent what requires a few minutes of writing down this expression. With this little sketch, I know immediately what I mean. Of course, I have to tell you what A is, and this is given by this expression. So the interesting thing is that what I discuss now, and that's what I think I will leave you with, it's some algebra that I encourage you to work with. I told you already, please, when dealing with vectors in a Fock space of bosons, verify explicitly that the normalization for a state which is n bosons is 1 over the square root of n factorial. Or if you multiply by themselves like this, 2 by 2, if you see here, follow this derivation step by step. You can prove in general that this is true by induction, by proving that this is true for 1, 1, 1, that is true if it is true for n, n is true also for n plus 1, n plus 1, and then you can prove it in general, that this is true. The way to do it is to remember the commutation rules, which is here, bb dagger is equal to 1 plus b dagger b, or bb dagger minus b dagger b, which is the commutator of bb dagger, is equal to 1. So from that, you can see that if I want to calculate the inner product between states 2, 2, what I do is I want to move this b, this annihilation operator, twice, here and here. Every time I move it, I have to use the commutation rule to express bb dagger in terms of b dagger b. This means that I have moved from the left, I moved it to the right of b dagger. And I'm left with a 1. And this is the one which I keep having. This will be this expression here, okay, for this object. And this gives me the 1 that I have exactly from this term, plus this object. I do it again, this gives me a 1 again. And so I get a 2. 2 factorial is equal to 2. In general, you can follow this derivation and do it for the state n, which is what I've done here, okay? So follow this derivation, and then what you see is what I told you before. The only matrix element which are non-vanishing here are those for which either I have a phonon, here I'm creating a phonon with momentum q and eta. I must have a phonon in a final state with this momentum q and eta. Here I'm destroying a phonon, so I must have a phonon in initial state, otherwise this would be 0. So the only non-zero matrix element for the term, I'm ignoring for now the Circe diagram, I'm considering this one in particular, I must have, okay, it can be non-vanishing, is a state, an initial state in which I have nq phonons with the momentum q. I didn't write the branch index eta, but I have 1 fewer in a final state. If this is not nq minus 1, this is 0, because this would be 2 eigenstates of the Hamiltonian, which is a remission Hamiltonian, corresponding to different eigenvalues. So it will be 0. So the only non-matrix element is this one. So ignore this for a moment. But what you have is that by using this process, this procedure, you find that this will give you 1 minus n of k plus q. The k plus q is coming from the fact that that I have the electrons over here. And for the phonons, I will have an nq, which is coming from the normalization condition of the states. So this is the electronic part. This is the same procedure except that I have fermions, so canonical anti-commutation rules. There will be a sign change occasionally. So this tells me that the only non-zero matrix element that I have, when I have a B over here, which means a phonon absorption, must have a state in which I have 1 fewer phonon in a final state. And for the electronic states, I must have 1 fewer electrons in initial state, of course. And this is Pauli's principle. The state of the final, in which the final K plus Q state in which the electron goes, this should be a subscript. I apologize, it's down here. Okay, must be available because of Pauli's principle. Okay, so the final state must be empty for the electrons. Remember that this n can be either 0 or 1 if I ignore spin. And then there is this coefficient, which is the Einstein coefficient, which tells me that absorption, when I take the square, which is I do in Fermi-Golden rule, the probability of absorbing a phonon is proportional to the number of phonons that I have around. If I do the same thing for the B dagger term, which is phonon emission, everything goes the same way. The electronic terms is exactly the same because there's no difference. The difference is in the normalization condition of the bosonic states, that rather than NQ, I have 1 plus NQ, which is kind of surprising, but that's the Einstein's coefficient. There is stimulated emission. This is coming from the canonical commutation rules. That's the ultimate reason why we have spontaneous emission. And NQ, which is also kind of surprising. Why should the emission of a phonon be stimulated by the presence of phonons? Same thing that we had for photons. And that's because there is a resonance. When there are phonons with momentum Q around, the system is encouraged to emit more because there are already phonons around. Exactly what happens in a laser, where you use stimulated emission to stimulate the decay of electron hole pairs and the creation of a photon at that particular wavelength. So this is the beauty of second quantization and dealing with the electron phonon Hamiltonian in this form. You get Pauli's principles and you get the Einstein's coefficient automatically out of the canonical commutation or anti-commutation rules. So that's another big consequence of the spin statistics theorem. So I will stop here. I'm running out of voice as usual, but I hope you understand the importance of writing the electron phonon Hamiltonian in this term. This is for short. I mean, just lump this mess over here. And the task that we have now is to get some numbers. How do we calculate this object? You will see that in principle, I can do it today if I use pseudo-potentials for my ionic potential. If I can calculate somehow the phonon spectrum, including the eigenvectors, which is really much harder, and calculate the eigenvalues correctly, then I can do this calculation and I can calculate the electron phonon interaction without any external empirical input. Whether that works or not is a story for another day, and we'll talk about it. But so I hope this is clear, how important it is, how the role of second quantization is important in this particular context, as in other contexts. It's the same thing that you see in quantum electrodynamics, the same story. Again, you get the Einstein's coefficients and Pauli's principle out of having second quantized phonons and electrons. And the intuitive representation of this interaction, I think, can be sketched by this diagram. I'll use them, talking about superconductivity. I will show some of these diagrams. And at least I think I know now, you should know what they mean. Okay, any question about what I've done? No? Everybody happy? Too complicated, too messy, too simple? All right, if there are no questions, no comments, no objections, then I wish you a good weekend. Stay healthy and safe, and see you next week.
Thank you, Max. Bye-bye.
Bye-bye.
Ciao, Massimo. Ciao.
Ciao, ciao.
Ciao Massimo.